Hello, everyone. Nice to see you. I remember this venue from doing a student party here a long time ago, but that's actually a different topic. I wonder where it is. Here we go. And we'll put this in motion. Just 1 second. Yeah, it should work. I think it should work. It doesn't work. That's fine. Good. We'll talk a little bit about graphs. Who knows a little bit about graphs already? Yay! Lovely. Who knows about Neo4j? Yay! Even better, right? So, because that's what we're going to talk about. I've been working with Neo for the past 7 years. Been quite a journey. We started in a shed in Malmö, Sweden, with 3 Vikings that wanted to build a database. How difficult can it be, right? And now we're 18 years later, and it's still not finished. But I'm very passionate about it. It's one of those things where when you start working with graphs, before you know it, you see them everywhere. Right? You see graphs everywhere, you see networks everywhere. And so I've been very actively writing about it. I can recognize the book example. You know, my book didn't sell either. The second one did, so that's good. You know, you can actually download that as well. Neo4j, like I said, Swedish company. We've been working on it in the graph space for quite some time, but we didn't really realize that it was a graph at the time, because at the time we thought it was a network engine for objects, right? And we were fans of the matrix, so why not? You know, that's how we ended up there. Been quite a journey since. So let me talk to you a little bit about graphs and graph databases. I'm hearing a big echo. Are you guys hearing that as well, or is it just me? Sorry. So let's talk a little bit about graph databases. So the first thing that I always have to do in explaining graph databases is, you know, we're not talking about graphical databases, right? There's so many people that confuse charts with graphs, right? And that's not what Neo4j and graph databases are all about. It's actually about structure. It's about data and data structure, right? And this all started back in the 18th century. I don't know if anyone knows this story. I'd like to spend 2 minutes on it. The 7 bridges of Königsberg, right? The name of Königsberg today is Kaliningrad. Kaliningrad, now you've learned something already. Come on, guys, this is happy days, right? Kaliningrad was a city in Prussia at the time. The Emperor of Prussia was coming to town. He wanted to take a tour of the town, but he was an emperor, so he can make silly demands, and he basically says, I don't want to walk a single street twice, right? Problem, because Kaliningrad is actually split into parts, into 4 different parts, connected by 7 bridges, and it's really, really difficult to take a walk through the entire town without walking a single street twice. They couldn't figure it out. They didn't know how to do it, so they called up this guy, Leonhard Euler, right? Leonhard Euler, living in Switzerland at the time, he of course says, sure, I'll help you guys out, but I am not walking any streets, right? That's not what I do. I'm a mathematician, so I'm going to look at this in a math kind of way. I'm going to look at the data in a different way, and I'm going to create a different data model for this. Right, this is really important, right? He looks at the same data, the map of Kaliningrad, of Königsberg, but he simplifies it. He creates basically the world's first graph, right? The world's first graph is essentially 4 parts of the city connected by 7 relationships, right? 7 bridges. Then he says, I can represent this as a matrix. This is an adjacency matrix. Matrices we know in math. I can calculate with this thing. I'm going to apply an algorithm, and I'm going to solve this effing problem, right? How does he do that? He counts. He counts because he realizes that if you're going to start somewhere in Kaliningrad, right, you're going to walk off of one of these parts of the city, cross the river, right? You're going to end your walk somewhere. You're going to walk onto a place in Kaliningrad, part of the city. But the ones in the middle have to have, you're walking onto it and off of it, right? So he realizes that the first and the last part of the city can have an uneven number of connections. The ones in the middle have to have an even number of connections, right? We're talking 1736 here, right? So he starts counting, and he basically sees that the walk is impossible. You cannot do it, right? You need another bridge or another part of the city. You cannot do it, right? Because they're all uneven, as you can count, right? Why am I telling you this boring story from the 18th century? Looking at the data in a different way, right? Looking at it as a graph, as a network, provides the essence of the solutions, right? And then applying some simple but meaningful algorithm on top of it, a smart algorithm on top of it, is actually going to get you there, right? And guess what? That's what we'll be doing with Neo4j all the time, but we needed another database for that. Right? Yes, we needed another database. 40 years of relational and all of that wonderful stuff didn't really give us the possibilities to do this. Why? Because basically there were two problems that remained, right, in the relational world. The first one you probably know very well. I see our friends from MongoDB are sponsoring the conference. They know how to deal with volume. They know how to deal with large amounts of data. Right? It scales infinitely, you just add more servers, horizontal scalability, ding, 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 and it just keeps on happening. And if everything goes well, you've solved the volume problem. Right? You can just add more data, add more servers. I mean, there's cases out there with literally thousands of NoSQL servers that work together in a cluster. Right? Great stuff. We've solved the volume problem because that stuff is not possible in the relational world. Right? You cannot buy enough licenses from Oracle to do that, right? So the other problem that remained was a complexity problem. It's a complexity problem about, how do I query data? How do I look for complicated patterns, right? If I'm looking for a restaurant in Antwerp on a Friday night, that's an easy question, right? But if I want a restaurant in Antwerp on a Friday night that's open to my kids, they have vegetarian food, my dog is welcome, and my friends have liked it, right? That's a little bit more complicated, right? You need more entities for that. You need more complex queries for that, right? That problem becomes very complicated in the relational world as well because joins, right? You need to do joins, right? Guess what? That's what NoSQL has tried to solve, right? In the NoSQL world, we've created all these different types of task-specific databases, right, that are really good at a couple of things, right? Not for everything, but for a couple of things. And this architecture of polyglossic persistence that makes it all work together, right? And GraphDBs basically fit into this complexity domain. We really want to solve those complicated queries with lots and lots of entities, deep traversals, complicated joins. That's what we do. This is not new. This has been around for a while, right? The first databases on the mainframe were actually graph databases, right? IDMS, IMS, those types of things. But they're coming back with a vengeance, I dare say, right? Why? Why are they coming back? Well, basically, I'm going to dumb it down, because that's me. I'm going to dumb it down to two reasons. Two reasons why graph databases matter and why you might want to take a look at them, right? The first one is modeling, right? Graphs, networks, as Euler showed us the first one just a little bit ago, are extremely good at highlighting, explaining, reasoning about complicated domains. Right? Why? Because we basically deal with these very easy to understand structures. There's only 4 building blocks. There's only 4 things that you need to know about. And they're all part of this structure called the labeled property graph. Right? The labeled property graph is the type of graph that most graph databases, including Neo4j, uses to store data. There's 4 parts. The first is these little balls that you see here, or nodes, or vertices, right? These little balls, they represent instances of entities, right? It's basically a person, a room, a hotel, a city, a chair, a computer, a microphone, a whatever, something, right? An instance of an entity. In a relational world, we would compare that to? That's a question. A record, yes, absolutely. A row in a table, right? That's what you should compare that to. These little balls, right? These little nodes, they basically represent one row in a table, right? An instance of an entity, right? They have properties, just like it has columns, keys, and values, right? And that's the second building block. It's properties. It's a property graph. We're going to store properties in it, right? The third building block are these colors, right? It's kind of like a special property of these little balls, right? They represent structurally meaningful properties of those little nodes, right? It basically says these things here are people. These things here are books. These things here are machines. They belong together. It's a structure, it's a color, it's a label, as we sometimes call it, right? It's a structural property of the graph, which we will use for things like security and indexing and all those wonderful things. Last but not least, the fourth element of the labeled property graph is the relationship, right? The arrows that you see in this little picture, right? They represent explicit connections between instances of entities. Rik lives in Antwerp. Lives in is the explicit connection that I have with Antwerp, right? It says something about my immediate relationship between myself as an entity and Antwerp as an entity. And it's not something that I have to calculate at query time. It's not like a join operation that I need to do at query time. No, it's explicitly part of the data model. It's something that I persist at write time. Right? At write time, I'm going to say this thing is connected to that thing. Right? And I'm going to do that, I'm going to store that, I'm going to make that an explicit part of my data model, which means that at query time, I'm hopefully going to save some time. Right? I don't have to calculate the join anymore. I have to find the join. Right? Very different operation. Right? So that's the first big part of why graph databases matter. This model, the labeled property graph, is a very, very significant part of why complex domains can be modeled so much more efficiently. The join tables are gone. Right? You don't see them anymore. They become relationships, explicit relationships between instances of entities. Right? So you don't have join tables anymore, and if you just compare the two pictures, you see that it's a much more simple way of looking at things. It's actually a much more human way of thinking about these things, which is why I had to come up with this new acronym: what you draw is what you store. Right? This data model, this network data model, I've told you before that I see it everywhere. After 7 years at the FJ, graphs are everywhere. But it's actually because we think that way. Our brain is a graph. We think associatively. We think in relationships. Right? So it's actually super easy for us to take this model to domain experts, ask them to explain their domain to us, and they will start drawing little balls and arrows. Right? So it becomes way easier to talk about domains instead of having to go through the complicated exercise of mapping a logical domain to a physical domain. Right? So another characteristic here is very relevant to things like pair programming or iterative programming or agile development in general. It's the fact that we don't really care about schema that much. Right? We separate the model from the schema. We believe that as you think associatively, as you talk to your domain users and find out more about their data, about their domain, you're going to iteratively develop the model, refine the model, and not necessarily want to cast that in stone in a schema. Right? So that means, you develop, and you add stuff to it, and you change things around, and you find out more information about the domain. And only when you get closer to production do you actually add schema, because that's when integrity and consistency really starts to matter, right? So there's a clear difference, and this is an implementation specific thing, but this is what we do. We separate the model from the schema. Second big reason why I think you should care about graph databases is performance. The modeling stuff, that's very fluffy, and long-term benefits and those types of things. This thing, if you try it out, you will see that it matters immediately. Why? Because I can do hundreds of thousands, and millions of joins on my laptop within a second, right? It's very, very performant for the simple reason that I'm talking about a completely different operation, right? I'm persisting the result of my join operation as a relationship, which means that I don't have to calculate it anymore at query time. At query time, I just have to follow the pointers. I literally only have to follow pointers. Computers are really good at following pointers, right? So that makes the join operation a completely different thing. Why? Because we use these two things, graph locality and index-free adjacency. We were trying to come up with an expensive sounding word to describe what we do. Index-free adjacency was the closest that we got, and it basically means that everything knows about its neighbors. If I find something in a GraphDB, in Neo4j, immediately I know what is connected to it. I cannot not know it. Right? So I know, if I find a node, I know what its properties are. If I find a node, I know what its relationships are. If I find the relationship, I know what's on the other side of the relationship, the node, right? If I find that node, I know what his or her properties are. You know what I mean? You go from one thing to the other thing without ever having to go back to the index, right? I only consult the index once at the start of the traversal, and after that, it is a pointer chase. Right? Really important, index-free adjacency, key characteristic of GraphDBs, and it's why they are lightning fast at join operations. Right? This is what we do well, complicated patterns, complicated queries, not the restaurant in Antwerp, but the restaurant in Antwerp that I like, that has vegetarian food, that my kids can come with me, and you know the story, right? So this is what basically kind of like the secret sauce, and obviously we try to make that as performant and high available as we possibly can. So where would people actually use that? Well, basically it's everywhere where you have these complex patterns. Everywhere where you can actually find these really complicated queries with not just one entity involved, but lots of entities involved. Anywhere where you have a lot of recursivity, like hierarchy structures or friend of a friend structures, those type of things, where you have a lot of recursiveness built in your querying patterns. And probably my favorite, pathfinding operations, right? Pathfinding is something that we all use every day when we use Google Maps and try to route our way around the city. But pathfinding is also something very meaningful in data. How is this thing connected to this other thing, right? How is this person connected to a system? How is this person connected to another person, right? If you're talking about things like fraud rings or recommendation systems, you want to understand the connectivity between two things without necessarily knowing what all the possibilities are, what all the hypotheses might be. You don't know enough about that, right? Our most beautiful example of that, I just watched a movie this week of the Panama Papers, the laundromat movie. I don't know if you've heard of it. It's fantastic. But in the Panama Papers, people were using Neo4j because if you're trying to figure out what the link is between the Kremlin and Panama, you cannot hypothesize about that. Those links are so indirect that you will not be able to come up with a suitable hypothesis, right? So you will never find it out unless you store it in a GraphDB and you just say, I've got this thing here, got this thing there, show me how it's connected, right? Because that's what it does really, really well. So we got these cases like recommendation engines. Someone that bought this also bought that, right? That type of an example, right? But much more sophisticated, obviously, and including things like price points, including things like logistical capabilities or supply chain capabilities or stock positions, those types of things. The real-time recommendations these days is a key use case for GraphDBs. Fraud detection, that's basically the same thing as recommendation engines, right? But it's, I recommend that you go to jail, right? That's kind of like the action that we're recommending there. It's very popular in financial services, but also in government use cases, insurance use cases, where people are trying to figure out these complicated rings. The fraudsters are smart enough to know that the single transaction should not be fraudulent. They know that. They know what the boundaries are, they know how to play that, and they're not going to get trapped in that. But what they do is they create these chains of transactions or rings of transactions that become fraudulent, right? So real-time fraud detection, master data management, you know, people in financial services, for example, or in government or other places, they care a lot about the quality of the data, understanding how to manage the governance of their data. And that means understanding where data comes from, where data flows to, and how you're going to assure that quality. Things like impact analysis, beautiful case with TomTom, but also other big organizations to understand the impact of a change in the network. Right? Something changes on the network, what is going to have an effect on the rest of the network? And sometimes that change actually doesn't create an effect or an impact in the immediate neighborhood. Right? So everything around it is perfectly normal, but over here, all of a sudden, something happens, which is what happens when you start editing maps and stuff like that. Which, similar to that is the IT network management use case, where big organizations are managing, or smaller organizations as well, are managing their IT or their network assets that way to make sure that they can troubleshoot it when things go wrong, to understand what the root cause might be of a problem, those types of things. And more we're looking at it in the context of access and identity management, security questions, right? Because, you know, we used to manage this in trees, like LDAP trees or Active Directory trees, something like that, but that doesn't map reality anymore, right? People are not structured into trees anymore, hence we need something a little bit more complicated. But I actually want to show you something else. I've got a couple more minutes, which is all about beer. Is that a good place to be? Yeah, I think so. Well, the story behind this is that when I started working for Neo4j, we didn't have a really nice demo data set, right? So it was all about Doctor Who at the time. And I was like, I don't know anything about that. Let me create a data set that I do know something about, and that would be Belgian beer, right? So I created this thing. You can download it. I've blogged about it. Oh, sorry about that. I've played around with it a lot. This is vanilla Neo4j server. Let me put this up here. And you can see that I've already done the import. I just took the Wikipedia page of all Belgian beers. It's a beautiful page with lots of beers on it. And I basically converted that very simple table in a very simple data model that has alcohol percentages, beer types, breweries, and beer brands. That's all there is in it. And I click on one of these beer brands, and all of a sudden I see, oh, this thing has 7.5% alcohol. It's brewed by the Proefbrouwerij in Deinze, I know that. And it is an amber beer. Okay, interesting, right? Now, what I did when I first started looking at this is I was looking, of course, for the beers that I love most, right? Which is, for example, something like Orval, right? The query language that you see here at the top, right, that's called Cypher. It's something similar to SQL, but it's for graphs, right? It's something that people use mostly with GraphDBs. So here we've got Orval. Orval is a Trappist beer brewed by an Abbey, 6.2%, and it's a brownish, sourish type of beer, right? 6.2%, that means it doesn't necessarily kill you, right? But it's still something to take a little bit care of, and it's a Trappist beer, right? Now, what happened to me, I want to show you this, when I first started playing around with this, is I saw Orval here, Trappist beer, right? Brewed by the Abbey, right? Other Trappist beers around here, and I saw this guy over here. And I was literally like blown away by it. What is that? Right? If you look at this, this is from the St. Sixtus Abbey, West-Vleteren. Anyone familiar? Right? They brew some really nice stuff, right? They brew the blonde one. I've tasted that. I've got the 12, which will kill you. And there's the 8, which is a little bit reasonable. But what is this thing over here? 6, the West-Vleteren 6, I've never had that. It's the same, alcohol percentage as Orval. I need to go and taste this thing, right? But as it comes out, this is the beer that the monks drink, and I'm not doing that anytime soon, right? So that was like my first epiphany when I started looking at this thing, just by browsing through the data, right? I didn't have any big domain expertise about beers. I was just browsing through the data, and immediately I look at this thing, and I'm like, wow, I didn't know that. Interesting. Which is when I turned my attention to Duvel, right? Anyone know Duvel? Be careful, kids. It will kill you again, right? So we've got Duvel over here, we've got Orval over here, right? Brewery, Moortgat Brewery brews Duvel. It's 8.5%. It's a blonde beer. It's a sugary beer, right? It's a Swedish type of beer, not Swedish, sweetish, right? And it's a high yeast beer. Now, what I wanted to know. And a typical question that people ask of graph databases is, what is similar between Orval and Duvel? I like both, right? Orval, sourish beer, 6.2%, Trappist beer. Duvel, sweetish beer, high yeast, high alcohol. How do they compare? How do they link up? Which is where I turn to my friend Euler and I say, okay, I need an algorithm for this, which is essentially a shortest path algorithm, right? And where is that? I've done this wrong, I think. Anyway, I'll have to do it myself here. So what I basically do is I grab the two nodes, right? Orval and Duvel, right? And then I say, okay, what I'd like to do here is I'd like to find the path, right, between Orval and Duvel. And I calculate that path with an algorithm called all the shortest paths, right, between B1, right, and I add a little star here, I'll explain in a bit, and B2, right, and then I'm not going to return B1, B2, I'm just going to return the path. Do you guys see what I'm doing here? I look up one node, B1, right? In this case, that's Orval. I look up another node, Duvel, and I say, calculate the path, right? That's all I need to do. I don't need to hypothesize about all the possible paths. I just need to see what happens, right? And this is fantastic. This was my second epiphany. You probably, I don't know if you can read it, right? So they've got Duvel on the left, you've got Orval on the right. High yeast is the red thing. 6.2% is the purple thing, and there's two beers in the middle here that I should be drinking right now. Actually, I've done that. Exeme beer, I can't get it anywhere. I don't know where to get it. Wildering Goud is actually a fantastic beer, and I love it to death, really. And I recommend that if you like Orval and Duvel, you should go and try out Wildering Goud. It's a fantastic beer. The only shameful thing about it is that the first bottle that I bought, I found it in a Dutch beer shop, which is kind of crazy. Anyway, that was my little example about graphs. I hope you enjoyed that. I see my time is almost up, so we'll take it from there, I think, right? Cheers.
Let's talk a little bit more about graph databases.
That's a good idea, always.
So, the beer example is already pretty compelling, I think.
I know.
And you already showed like fraud detection, but what are other good use cases you've seen, and what is like the most exciting use case you've seen yourself?
I'm so torn by that. I mean, I'm very lucky to work for Neo4j and see a lot of different use cases.
Yeah.
But in the morning I'll be talking to a pharmaceutical company, in the afternoon to a bank, and at lunchtime I'm talking to a startup. It's very diverse. The one that I like most, I think, is very telling of the power of graphs. I don't know about you, but I know a lot of people. I'm 46 years old, and I'm starting to get to that age where people are starting to die around me, right?
The beer example was more fun.
Yeah, I don't know, but I want to talk about cancer research, actually.
Okay.
Right? Cancer research is one of those things that is dear to my heart, and people are applying graphs to cancer research. Is anyone familiar with PageRank? The Google algorithm for ranking web pages when you search for them. Well, it turns out that people are using the same algorithm, exactly the same algorithm, to rank tumor cells.
Wow.
Right? So you've got a tumor, right? And turns out that in a tumor, not all cells are created equal. There's some cells that are so connected to other cells that they cause the metastasis. They create the problem.
Yeah.
Right? So you want to target those types of cells in your treatment.
Yeah.
Right? And that's a fantastic, mind-blowing example, I think, of how looking at the data just in a different way and applying an algorithm to it, it's just extremely powerful.
Yeah, that's impressive, and it proves how far you can take
Oh,
it and how
can.
useful it can be. Now, if I want to begin with graph databases, what are some good resources that I should check out?
Well, first of all, Neo4j is obviously a commercial company, but we are huge believers in open source.
Okay.
We organized, actually, I'm very proud of this. 2 weeks ago, we organized our first online open source conference. We had more than 5,000 people register and 1,800 people attend. Wow. 61 viewing parties. I mean, that's just crazy great.
That's cool, yeah.
And so if you want to start with graphs, you just play around with that. You just download the open source version. It's packaged. I mean, everything I showed you is just available for free.
Yeah.
There's nothing payable about it. It's you get around. There's a community website with a lot of material on it. There's free courses there. So that's where I would start, and take it for a spin. Try to load some data. Start with 3 billion records and expect for it to load in 2 seconds. That always works. Yeah. That's not true, by the way. And then you start playing around.
Okay.
Yeah. And if you have problems, you call us.
Cool. Thank you. That's all we have time for.
Yep.
May I have another applause? A round of applause for Rik.